I'm Georgia and I'm a chemical engineer, and I work as a PhD student in the University of Strathclyde, and specifically at CMAC. CMAC tries to jump from batch to continuous manufacturing. The title of my talk is Determination of the Supercritical CO2 extraction drying endpoint using SIFT-MS analysis. The fact that we can use SIFT-MS online can give me the endpoint, let's say, of the extraction, so my process becomes more efficient, so I can obtain dry samples without spending CO2 and more time. I used before GC, gas chromatography, to analyze my samples, the same samples that I analyzed with SIFT-MS, but it wasn't very easy to get consistent data because we had to prepare standards to create calibration curves, and we had to reach really low concentrations, so it was quite difficult, and though they cannot dissolve very easily to polar solvents. So for me the most important, first of all, is that we can use it online in my process, and so we can monitor, let's say, at the later stages of the extraction, the process, which is the most intriguing part of my project. And the second, of course, is that it doesn't involve sample preparation like GC, because we had many issues with that. So it's very direct and quick, and we can get very easily information. It's an interesting event because there are people from different backgrounds here, and you can see that SIFT-MS can have many applications in different fields. Because I wasn't very familiar with analytical techniques, and to be honest, I had no clue about SIFT-MS before, and how the technique works and everything. And there are people actually that they are using it in biomedicine, in food industry, in pharmaceutical, like me. And in many other applications, so I found it very interesting. I'm here today to talk about how SIFT-MS is applied to my project. So, as everyone knows, the production of a drug product is a multi-step procedure that includes synthesis of the drug substance, crystallization, filtration and washing. And here is where my project fits in the pipeline, and supercritical CO2 extraction comes to replace conventional drying. And the last step is formulation and dissolution. So why it's important to find alternative ways of drying? Generally, there are many conventional drying issues. The most important ones are the solvent residues in the final sample, even after long drying times, sometimes take days. High boiling point solvents demand high temperatures that lead to product degradation, and incomplete drying results in agglomeration. While with supercritical CO2 extraction, we aim to minimize the solvent residues in short time scales and at relatively low temperatures, and the complete drying eliminates agglomeration. So before we started our experiments, we had to design our experimental plan. So first we defined our system. We used as a model compound paracetamol, as a crystallization solvent IPA, and as a wash solvent dodecaine. Dodecaine is the main solvent that we are extracting. It has high boiling point, 216 degrees of Celsius, and it's very difficult to remove with conventional ways of drying. As a filtration method, we chose vacuum because it's widely used in industry, and as a drying method, of course, supercritical CO2 extraction. So the most important factors that affect the extraction kinetics are the pressure, temperature, and CO2 flow rate. The conditions were selected with respect to the critical point of the binary system dodecaine and CO2, and in this case is 71 bars and 40 degrees of Celsius. And as fixed factors, we chose the cake size, which in this case is 60 grams, the volume of the wash solvent, and the paracetamol grade, which is powder. To design our experiments, we used MODE software, and we chose the full factorial experimental design. So each corner of this tube represents a combination of the three factors, pressure, temperature, and flow rate, accompanied by three center points. The responses that we are really looking at are the mass transfer, the moisture using loss on drying, residual solvent using SIFT-MS hedge-based analysis, surface area using adsorb extraction time, agglomeration, agglomerate plateletness index using sieving. And we also did XRBD analysis to check the structure of the paracetamol before and after the supercritical CO2 extraction. So in this slide you can see a schematic diagram of the process. So as you can see, there is liquefied carbon dioxide pumped through a heat exchanger and is introduced to the pressure vessel. There is a back pressure regulator after the pressure vessel that maintains constant the pressure while we have a continuous flow of the carbon dioxide. And the CO2 solvent mixture is led to the cyclone, where the conditions there are quite low, and we have separation of the two phases, so the solvent precipitates and the CO2 goes to the exhaust. Here you can see pictures taken from the setup that we have available in the labs at TIC. So in the left picture you can see the bottles, in the next picture is the supercritical CO2 ring that is constituted of 4 different pressure vessels, each of them finds different applications. And there is also software that we can monitor our process. So for all the experiments, exactly the same methodology was followed. So we prepared the 60-gram paracetamol wet cake in the basket. We took the basket, we placed it inside the chamber. Then we defined the desired supercritical conditions, and we run the process. And we take measurements by weight the loss of weight of the sample at different time intervals. So what we do is we stop the process, depressurize the system, take out the sample, wait, put it back, pressurize again, and do that till the mass of the sample doesn't change, and we can say that the extraction is done. And from these measurements, we generate extraction curves. Here there is an example taken from the literature. So you can see the percentage of the extracted solvent versus time. These extraction curves are separated in 3 different zones. We have the fast, the transition, and the slow zone. In the fast, we remove the easily accessible solvent, and in the transition and the slow zone, we remove the solvent that is trapped between the particles or in the crystal structure. So from our experimental data, we generated our extraction curves, and we could obtain very useful information about how the pressure, flow rate, and temperature affect the extraction kinetics. So in the first graph, 2 experiments were conducted at 50 degrees of Celsius and 10 grams per minute flow rate, but we chose 2 different pressures, a high one and one close to the critical point. So 200 bars was the highest and the lowest was 80 bar. The 200 bar corresponds to the yellow line, to the yellow curve, and the 80 bar to the black one. So as you can see at 180 minutes, or you cannot see because the numbers are really small, at 200 bar we managed to completely remove the solvent, while at 180 minutes, at 80 bars, we removed only 20%. So definitely we can see that the pressure, high pressure facilitates the extraction kinetics, because high pressure means high density of the carbon dioxide, and more CO2 molecules interact with the dodecaine. In the second graph, we studied the effect of temperature. So we chose 2 different temperatures. 70 was the highest and 50 was the lowest. We didn't observe any particular change in the behavior of the system, but generally we know that there are 2 different phenomena that take place at the same time. The high temperature increases the vapor pressure of the dodecaine, but at the same time decreases the density of the fluid. And in the third case, we studied the flow rate, the effect of flow rate, and it was what we expected. 30 grams per minute was the highest and 10 was the lowest grams per minute, and high flow rate facilitates the extraction kinetics. So in this table, we present all the experimental results that we got. There are highlighted rows that you cannot see, but we rejected the low conditions, the conditions that they are close to the critical point, which correspond to the 80 bar. And these were rejected because or we had incomplete drying after 5 hours, or we had complete drying within 5 hours, but we spent lots amount of CO2, about 8 kilos. So these were rejected. But above these conditions, at 140 bars and 200 bars, we managed to remove 20 grams of dodecane within 2 hours and reach really low concentrations of dodecane and IPA in the final sample. In some cases, we had 0.8 ppm and 0.7. And we produced soft agglomerates, and we spent around 2 kilos of carbon dioxide. So in the also there is an optimizer tool provided from the MODE software, and it gives us the best combination of the factors that optimize the extraction process. And in this case was 200 bars, 70 degrees of Celsius, and 10 grams per minute flow rate. In the second part of my presentation, we combined SIFT-MS with the supercritical CO2 extraction process. As everyone knows, SIFT-MS measures volatile organic compounds in the gas. It has high sensitivity, can detect parts per trillion, and can be used online and eliminate sample preparation. So we had to modify our process, connected a stream after the back pressure regulator to SIFT-MS. So we can, by using online probe, we can take samples after the exit of the pressure vessel and measure the concentration changes in real time. So we did some preliminary tests before we start a new DOE using the SIFT-MS. So we changed only the methodology, the size of the sample. So we increased the size of the cakes to 120 grams of wet cake, and also we changed the way of taking the measurements. So in this case, we weighed the solvent collected from the cyclone at different stages of the extraction cycle. So, as you see, we got more data points using this methodology, but while we are reaching the end of the extraction, we extract traces of solvent that they are very difficult to collect from the cyclone and weigh them with the mass balance. And this is where we apply the SIFT-MS, and we use the probe, and we can track the concentration of dodecane that decreases over time, as you can see. And after 65 minutes, it reaches a plateau, which means that no more extraction is happening, and we can stop the process at 75 minutes, and we can add the end point of the extraction to our curves. Also, obtaining more data points, we observed that at the beginning of the extraction, the process was quite slow. So we did some assumptions. Basically, we thought that the system didn't reach the temperature quite fast, and that's why the extraction process was quite slow at the beginning. So we did 4 different experiments. In the first experiment, the extraction started directly. And in the second one, the extraction started after leaving the cake for 30 minutes to reach the 60 degrees. And in those 2 cases, the extraction was quite slow. So the fast extraction zone starts after around 40 minutes. While in the third experiment and the fourth experiment, that we left the cake to preheat, we preheated the cake for 1 hour and 1 hour and a half. the extraction curves are shifted to the left, and the fast zone started after 20 minutes. And generally, the total extraction time in the third and the fourth experiment is reduced by half. So definitely, the process is more efficient using preheating, and we spend less carbon dioxide. Also, we compared the two methodologies, the one without the SIFT-MS and the one with SIFT-MS, using SIFT-MS. So in the first case, we extracted 20 grams of solvent within 2 hours, and we spent 2.5 kilos of CO2. While using SIFT-MS and changing our methodology, we extracted 37 grams of solvent within 1 hour and 20 minutes and spent less than 2 kilos of carbon dioxide. Afterwards, we analyzed the samples in the lab after the drying process. So we took a few grams of the paracetamol, of the dried paracetamol, and we placed them in the vial of 20 ml, and we left it to reach equilibrium, and then with a syringe of few ml, we took a sample of the headspace and we injected to the SIFT-MS, so to have a quick look if the samples are dry or not. So we generated these graphs, and in all cases the dodecane was approximately 0, but these measurements were at the room temperature, while the isopropanol was between 100 and 160 ppm. But in all cases we can say that the sample reached the drying point. And then the samples were sent to Mark, who had to analyze them further. So what he did is take few milligrams, around 200 milligrams, and incubate them at 80 degrees for a few minutes. And then he took samples from the headspace, and these are the results. So in all cases, we had approximately 4 to 7 ppm of dodecane in the samples, and the isopropanol was around 4 ppm. So you can see from this graph that both techniques are consistent separately and coupled together. So to conclude, using SIFT-MS, we can determine easily the endpoint of the extraction process, and we can change our methodology and spend less CO2, get more data points, and the extraction is faster. And also with SIFT-MS headspace analysis, we can have a rough approximation of the solvents if the sample is dry or not. From my experience, I can say that it's easy to handle, and it's a robust tool, and it can find many applications in CMAC because we try to jump from batch to continuous manufacturing, and we try to develop PAT tools that can be used online. So definitely is useful. And I would like to thank my supervisors and all the tires that fund this project, and Anna Thune that gave me the opportunity to use SIFT-MS, and Mark for his help and use for your attention. Thank you.
Thank you very much, Georgia. Has anybody got any questions?
I've always got one.
So I look at you.
So the solvents you're looking at the moment are things like dodecane and IPA. Are there less common solvent systems that you would be interested in that SIFT-MS potentially could handle?
Yes.
Because it can obviously do lots of things.
Yeah, we have a small list, let's say, in CMAC, because we use specific solvents for our projects. But they are less common in industry. So, like also DMSO, for example, it's one example that I'm gonna use and try to remove it. And it's very difficult, generally, to remove it with conventional ways. So that's why it's not very common and it's not used so much in industry. But yeah.
So obviously the kind of the driver for this kind of work is to go from batch pharmaceutical processing to continuous.
Yeah, the general idea of CMAC is that, but my project at the moment is a batch or let's say semi-continuous process, because you extract continuously the solvent, but you have to place the sample, dry it, and then take it out. But in the future, probably, if the technique works and we see that energy-wise is viable, we're going to try to find a patent so we can make it continuous. We have some ideas for the future, but still we are not very sure, because we use high pressures and it's not very easy. It's a closed system.
Yeah.
So it's quite difficult, and we need to scale up as well. So.
Yeah, sure.
Yeah. How low was the detection limit for your dodecane?
So the detection limits that we have in the lab, so the maximum is 100 ppm, I think, and the lowest, I mean, it's parts per billion, but we haven't reached below.
No, I mean, I can I did some work on the finished dried products, looking for things like IPA, dodecane, etc. And we were on the really clean, dry stuff. We were seeing dodecane at tens of parts per billion. So the end point on this system here is nowhere near the bottom endpoint instrument capabilities at all. So it's clear from, I think that Georgia can back me up on this, is that the end point is defined as when the process becomes inefficient. So you spend lots of time and effort and you're just not removing anything, as opposed to the end point being defined on the concentration, on the sensitivity of the instrument. The instrument is much more sensitive, so the end point is the process becomes inefficient at that point.
Yep.
And so it's a good, my take on this is it's a good instrument for detecting that point when those processes plateau out. But it's a long way above the instrument detection limits. I think interestingly, this feeds into a sort of more broad sort of analysis about residual solvents in pharmaceuticals anyway, and where you can see where your residual solvents now come from to some extent, is that, you know, these endpoints are difficult to dry out completely. So yeah. I think, is that right?
Yep.
So, yeah.
Yes.
Any more questions for Georgia? No? Okay, cool.
Thank you.